Okay, MMI711 sequence models in multimedia, and we are going to talk about recurrent encoder decoders. It is something we have already started talking about, encoder decoders, but we're going to delve deeper into encoder decoder models, and we are going to talk about and study some practical code about recurrent encoder decoders. I mean, where both the encoder and decoder will be a recurrent neural network. Which is the actually de facto standards for sequence-to-sequence models in NLP and other categorical sequence models. I emphasize on this categorical, not signal-based, categorical. Okay, let's continue. So this week is recurrent encoder-decoder architectures. ED, encoder decoders, is widely used in deep learning in many different fields. Actually, the RNNs that we saw previous week was a type of encoder-decoder networks, because what we did was we've managed to extract features from a convolutional neural network. So we carried the representation to a higher level using an encoder. That's what encoders are for. And then we used an RNN to model the sequence, because it was a sequence. The problems the problems you solve with CRNNs are sequence. That's why they have a strong place in this course. So the ED models, recurrent ED models, are usually generalized as sequence-to-sequence models in deep learning, especially in NLP. So these will be the titles. So let's talk about encoding, decoding. For some of you, traditionally, the idea of encoding may be familiar. For some of you, it is not. Actually, it comes from engineering, and especially electrical engineering. Encoding and decoding is used in communication, but not as usual telecommunication. Any type of communication that you may come across in a digital system, like when you're communicating between some graphic card of the computer to the main board. I don't know. You're sending some information from somewhere to another place. You encode or decode for many purposes, for efficiency of bandwidth and other reasons, okay? So it's usually optimal transmission or storage, because when you encode something, you carry that information in a higher level, which is an efficient way of storing it and also transmitting it, because it may take a lot of time when you do not encode it when you send the raw data. Okay, so it's like compression. But the thing that we're going to be doing is actually carrying the signal or the sequence or the categorical data that we're using to a higher level so that it can be represented as an abstract feature or as a sequence of abstract features in our case. Okay, so in computers, the encoding is the process of putting a sequence of characters, letters, punctuation, categorical data, or sometimes signals into a specialized format for efficient transmission and storage. And decoding is the opposite. So you just do the reverse operation so that you got the signal or the data back. Signal, that's so simple. So different scientific fields use it. I mean, to start with telecommunications, the most, networking, programming, and also we do, machine learning do. But as again, we do not do it for compressing it or decompressing it. We do it to understand the high-level features. Okay. You know this actually. This was what we have done in the previous week using CNNs and RNNs, but we are kind of trying to generalize the idea here, because it's kind of a very general idea. And most of the deep learning architectures today, state-of-the-art architectures, are actually encoders and decoders. In the end, they are very complex architectures, but when you see it, a large part is the decoder and another part is the encoder. So encoder first, of course. So the idea is, by using an encoder, you carry the data or the signal, depends on the nature of your problem, is carried to an internal representation. Sometimes we call it the latent representation, because there's less data compared to the input. But it's at a higher level. I mean, it is like looking at a picture, but not saying it's pixels, but saying about there's a face, there's a blah, blah, kind of the CNN encoder idea. But this is, of course, different for sequential encoders, because when you are trying to get an internal representation of a sequence, it is not that signal information you get from an image. It's somewhat different. It's, for example, if the data is Bitcoin prices, then maybe the general trends could be an internal representation, which is in between. It should be, in my opinion. And more importantly, this internal representation is usually not transparent. I'm giving you some examples that you might make a meaning of, but that's not necessarily the case. I mean, the latent representation is usually something we don't understand. It's like the hidden states of an LSTM. It's actually in the early encoder-decoder models that we're going to be covering today. They are the hidden states of a LSTM, nothing more. So you don't understand anything about it. But encoder and decoder, they do. Okay, so in order to give you the idea of what encoder and decoders are and the hidden state, the game of drawing pictures, I think it was Pictionary. Pictionary is a very nice example because one person is trying to give you the idea of a word to the other person, but they're using an internal representation, which is a drawing. This is a transparent representation, but it's transparent between these two people. So if you were a blind guy, two people playing Pictionary would be like a sequence model for you because you don't get the internal representation. They somehow pass the information using some data representation you don't understand. You cannot acquire. So that's a perfect example for how it will come to us. I mean, people, when it comes to recurrent encoder-decoders, because we won't be able to make a meaning out of the internal states that pass between the encoder and decoder, but we will be sure that it's passing, like the blind guy hearing people playing Pictionary. Okay, so just like before the previous week, we have talked about the CRNNs, and we said that CNN plus RNN is a type of encoder-decoder. But there are even different types of encoder-decoders as well. And I think you are familiar with this since this is not the first deep learning course you're taking. In the introductory level deep learning courses you have taken, there were CNN encoder-decoders, both parts being convolutional. And the most common example is the semantic segmentation, when you're trying to pixel-wise label an image or a signal. So when you're trying to classify different regions of a signal, pixel-wise labeling is finding the class of each pixel. Imagine you have satellite images. Do I have an example? No. So let me draw it to make it more. I mean, some of you already know this, I'm sure, but for those who doesn't know, so you have it. Sorry. It's not drawing. Sorry. So you have an image here, you have an image, there's a guy here, and there's the sky here. So in the output image, what you do is you classify. So you say this is the, these pixels belong to the cloud, or these pixels belong to the person, kind of. So you are classifying each pixel. So that's how you do it. I deliberately draw them in different colors, so to give you the idea of pixel-wise classification. But this is not necessarily an example for images. For sound, for example, you are trying to segment the regions of a sound. It's just called speaker diarization. So who is speaking when, kind of. It's also a type of semantic segmentation. And for that purpose, we are using encoder-decoder models in deep learning. I think this is something you already know. So these are also called encoder-decoders, and the UNet architecture is a famous encoder-decoder architecture for convolutional neural networks, or the SegNet. In both of these architectures, the common idea is you have an internal representation, and there is something passing between the encoder and decoder, not only the internal guys, but these indices as well. The examples we are going to be covering today for recurrent encoder decoders will be passing only the latent representation, not like these indices that SegNet does, but actually making a relation between some parts of the input, some hidden values, the states, hidden layers of the input to the hidden layers of the decoder to hidden layers of the encoder is a fantastic idea, because when you do this in recurrent neural networks, it will generalize to the idea of attention. But this is not something we're going to be doing today. We're trying to understand the evolution of encoder decoders from only convolutional networks to only recurrent neural networks. Okay. So, for example, this is a semantic segmentation example, the thing that I was trying to draw. So I'm glad that we have a real drawing here. So each pixel is labeled with a color. But not only semantic segmentation. For example, yes, another important thing. So I was providing you examples about semantic segmentation. However, just like I said in like a couple of slides back, nearly almost all deep learning architectures today are encoder decoders. For example, the famous YOLO, which is not a recurrent architecture. It's a complex convolutional architecture. Not only convolutional, it has some special layers as well. This is not the scope of this course, but I'm sure you have seen this in the previous deep learning course you've seen, or you have come across this network. It is an object detection network, which is actually comprised of some encoder and decoder. So somehow in today's deep learning architectures, recurrent or not, it always boils down to encoder-decoder architecture, because that's what we are trying to do. We are first trying to understand the abstract features, the meaning, the latent representation, a semantic out of the signal or the data. Then we use that internal representation to construct the output that we desire. If it's a detection network, it's detecting. If it is a sequence model and creating a sentence, that's the output sentence, nothing else. Okay, so, and one more thing, it is important because we are going to be talking about recurrent encoders today. All autoencoders are encoder-decoder models. What is an autoencoder? If you've taken a machine learning course, or if you've taken an introductory level deep learning course, you most probably have seen this. Autoencoders is a type of model where the signal or the data is encoded by itself. So what you do is you train a network, just like the units, or it could be different, where there is the encoder and the decoder. While you're training this network in a supervised fashion, the input and the output are the same. So for each input, the ground truth is itself. So what you are trying to make this network learn is to learn a representation in between, which would represent the training set properly. This is called autoencoders. You're auto-encoding the training set. What would the effect of an autoencoder will be is, what would the effect of an encoder be is, it is you use a large training set. You are finding the common features, common abstract representations that exists in the signal set. So will it work for recurrent, will it work for sequences? So can we think of recurrent encoder decoders? Actually, yes. There are recurrent encoder decoders, and they are being widely used for many purposes, one of which is anomaly detection. And we are going to talk about this today in the following slides as well. And there is this, an advanced version of variational autoencoder, because autoencoder is something that encodes the input signal, the training set only, but maybe you're trying to generate some different examples. I mean, some outliers, even outliers to the training set. Then what you do is you make some variations in the latent space, in the internal representation, and send the representation by making those variations to the decoder. So you obtain different kind of images. That's called variational autoencoder. That's the idea. And this also can be applied to sequence models. So this is a generative model, encoder decoder, variational encoder decoder. So autoencoders are mainly used for encoding a large corpus of data. However, variational autoencoders are used to create some new examples out of that training data, like a generative model. Okay. So I'll get back to recurrent EDs. Recurrent EDs are also usually called as sequence-to-sequence models as well, because they are being widely used for modeling sequences. And I mean, where the input and the output is also sequence. That's why it's called sequence-to-sequence models. But remember, when we say recurrent EDs, we mean sequence-to-sequence models. So when somebody says sequence-to-sequence models, you can directly understand it's a recurrent ED. However, not all sequence-to-sequence models are recurrent. Recently, we have these transformers, which are somehow not entirely recurrent. The encoder is not a recurrent architecture. But traditionally, when we say sequence-to-sequence models, we are talking about recurrent EDs. This is changing, of course. I mean, recurrent EDs, these sequence-to-sequence models, are the ancestors of transformers. But there's an evolution there as well. We are going to be talking about vision transformers in this course in the following week. So I'm trying to give you also a perspective about how that evolution of architectures also change. Anyways, encoder-decoder models for sequence-to-sequence problems have recently achieved significant results. Well, that's true. I mean, in the next hour, I'm going to be showing you a machine translation example in PyTorch. And actually, it is like 6 years old only. And it only uses LSTMs and fully connected layers. And fully connected layers are 50 years old. LSTMs are more than 25 years old. But this architecture is only 5 years old. It's kind of a recent trend on EDs, but they work very nice. They are being widely used in different problems, starting with machine translation, where you have a recurrent model at the encoder and a recurrent separate model at the decoder. Please note that these representations are unrolled in time. So this is, for the sake of simplicity, the example given in this figure is a single recurrent model, which is calling itself. Okay, this is a single recurrent model. Maybe it's a vanilla RNN, maybe it's an Elmon, maybe it's an LSTM, doesn't matter. Where the encoder, where we call this part the encoder. And the output of this model is the final hidden state that was obtained when you fed a sequence of inputs. So the final hidden state of this first recurrent model becomes the latent representation. It is like that latent representation evolves and gets a shape by given some sequence inputs, okay? Actually, this representation is fed to the second RNN, which is used to decode the output, which is also a sequence, and you get the output. And usually, this vector in between, it doesn't have to necessarily be the hidden state output of the first model, but the simplest model will implement this idea like this. Actually, that's exactly what we're going to be doing in the next hour. So imagine this is an LSTM, this is an LSTM, and this is the hidden state. We also call this the context vector, because for this sequence-to-sequence problem, where you have the input as the sequence and the output as a sequence, the context, the semantics, the meaning that the input sequence carries will be embedded within this encoder vector, or also called the context vector. Context vector is widely used in this literature. I mean, it's also related to databases and that stuff as well. So when we learn about transformers, it's going to also be called context vector. Or when we talk about attention in the following weeks, it's also going to be called the context vector, this internal representation. Okay. So in this example, the recurrent encoder is a stack of several recurrent units. Maybe a single LSTM, maybe a multiple LSTM, doesn't matter. It's a stack of recurrent units. But even a single LSTM will make an encoder. And it does. I mean, it does a pretty good job, actually. For example, what kind of a problem can we think of? For example, in a QA problem, question answering problem, it's like machine translation. The input sequence is a collection of all words from the question. Hello, how are you today? Imagine I'm trying to talk to a computer, I'm just trying to get a small talk with a computer, that would be my question. So the words being passed to this LSTM. How the words are being passed, they are somehow embedded to a vector representation, which is called the word embedding and blah, blah, which we are going to be seeing an example of in the next hour. And here the context vector will be, just like I said, if it's a simple LSTM representation, the hidden states that I obtained when I fed the last piece of the element of the sequence. I could use a more complex hidden state. I mean, maybe I could just concatenate all the hidden states from the previous sequence evolutions. I can do that. Actually, there are studies that way. But in the end, the idea doesn't change. I create a context vector, which was constructed by feeding the input sequence to a recurrent model. And in a simple example, it may act as an initial hidden state for the decoder, just like the show and tell example. Remember, in show and tell example, the initial state of the recurrent decoder was the features obtained from the final fully connected layer of the VGG. Not it was for show and tell, it was the Google Net, but whatever, it doesn't matter, the CNN. Good, and the decoder is, again, a recurrent architecture. It could be a single LSTM or a complex architecture, it doesn't matter. For example, for a transformer, it's a complex architecture with feedback, some sort of feedback. So the output would be the answer for that particular question. And the only thing I feed about that question to this decoder model is the meaning here, the context. Nothing else is passed. I mean, I'm not saying nothing else should be passed, but in the simplest encoder-decoder representation, recurrent encoder-decoder representation, I can model it this way. And I repeat, this is the example that we're going to cover in the next hour in the live code, because that would be enough. It kind of magical, sounds magical to me, but it works. So I somehow embed the information of the input sequence to a context vector, a single vector. Then I feed that to the decoder recurrent architecture as a hidden state, and it creates another sequence for me. But this does not have to necessarily be an NLP example of question answering. It could be another kind of NLP example. For example, I don't know, machine translation, of course. Or it could be some sort of different NLP example. It doesn't have to be necessarily an NLP. But in the end, if you're using some categorical input sequence like text, it boils down to the practice of NLP. So actually, we can safely say that recurrent encoder-decoders, these sequence-to-sequence models, are a kind of applications of natural language processing, NLP. That's why actually we are going to cover these, and we are going to cover these because we are trying to understand the evolution of these algorithms until the vision transformer and some other architectures as well we are going to see in this course. However, there is another course actually covering these subjects in a broader fashion, which is Tuğba Hoca's text analytics course. I strongly recommend that course to those who will be dealing with NLP models, categorical sequence models in their studies, theses, PhDs or masters, whatever. Okay, so this is like an introduction, but for the real stuff, you need an entire course on deep NLP, in my opinion. Let's continue. So just like we said, what we are trying to do is we are trying to carry the sequence, input sequence, to an intermediate vector representation. We can say that it is language-less semantic, just the meaning, so that it's going to be translated. Okay? Just like the example. When Google's translate is quite good with slang as well. When you say Nabella, it's quite the representative form in English like what's up. And it does it. Somehow, the context vector carries this information as well. Whether it's slang or not, information is also embedded within. So think of the context vector like the deep semantic of it, the way the machine understands it. Good. So just like we said, the previous week's practice was an encoder-decoder, where the encoder was a convolutional model, where the recurrent decoder was a recurrent model. However, in the end, this representation here, which is being fed from the GoogleNet, was the context vector, okay? To the decoder. So that would never change. In the end, in an encoder-decoder model, we are passing that information. Actually, that's why we are using the encoder-decoder model. We are trying to construct that language-less semantic representation, okay? And actually, in human memory, in cognitive science, there's this concept of two types of memory. If you're coming from cognitive science background, I'm sure you're familiar with this. There's the episodic memory, the way we understand things in an episodic manner, in a linear chain of time. And there's the semantic memory. Semantic memory is like how you keep the feeling of a breeze or the taste of an orange. That's a very, very deep internal representation. The context of breeze, or context of orange. That's what we are trying to get here, the semantics of a sequence, and keep it so that when we feed it to another decoder, we are going to use it. And remember, before I pass to examples of different sequence models, remember, when you're using an encoder, you can feed it to different decoders as well, which will act for different problems. So it is important that you keep that internal semantic representation and use it for a necessary purpose with different architectures of decoders. Again, image captioning was a nice idea where you had the latent representation. And as again, the all RNNs of the previous week was EDs. And all of those examples actually had a context vector being fed to the decoder, which was a latent representation. Well, there is no exception for that. When we talk about sequence-to-sequence models, or when we talk about encoder-decoders, there is a semantic latent internal representation that you feed from encoder to the decoder. That's the idea. That's the defining idea of EDs. Okay? So we could also talk about video captioning models. Again, we have the raw videos, but in the end, you had an internal representation, nothing else. And that latent representation is what is happening in that video. Well, what is happening in that? When I ask you to caption a video, your output are words or sentences. Okay, you construct sentences. That's your decoder. But that's not the internal representation. I mean, think of a person who is very bad at expressing themselves. And they cannot construct a sentence. I mean, there are people like that, people who read less, or people who, I don't know, have less education. When you ask them to describe something, like a video, what's happening in the video, they sometimes don't know what to tell you, but they do understand what is happening inside. So they do have the internal representation. So they do have a working encoder. But how you express it is actually the job of the decoder. That's why there are two separate parts. So when we model our sequence-to-sequence models, sequence-to-sequence problems, just like describe that video for me, we need two separate things, where the encoder is like a very instinctive thing for humans, and it's going to be for the machines as well, but the decoder is more like a sophisticated output machine. Okay. ED frameworks of video captioning techniques have four major models, by the way: CNN encoders, feature transformation, you get the features and transform them. You have the word embeddings for the decoder and the language model for the decoder. So this part is the encoders, decoder. Okay, so I will get back to recurrent encoder decoders again. Actually, machine translation was the first example that kind of worked best for recurrent encoder decoders. I mean, in 2014, maybe you remember that day. I mean, we can all remember that day. Someday, people were talking about Google Translate, and the fact that it started working very good. I mean, today it's even better because they are using more complex architectures. But in 2014 or 15, I don't remember exactly how it was operationalized in Google's interface. But these guys from Google, these are, you all know them, celebrities, Skever, Vinyals, other people. They have come up with this idea of an encoder and decoder to translate text to another language. And it was pretty successful. And the funny thing is, just like I said, like, I don't know, 10 minutes ago, it was a very simple design. It was an LSTM fed to another LSTM, then a fully connected layer. I mean, fully connected layers are more than 50 years old, and LSTMs are a quarter century old, 25 years old, more than. So how come we could think of it like 5, 6 years ago? Because the idea of using encoders and decoders for sequence-to-sequence modeling could evolve until then. So it's simply, this is a recurrent model unrolled in time. This is the end of sentence, and this is the latent representation you feed to the decoder. So when you have a decoder, you are feeding the output of the current output of the decoder to the next state of the decoder as the input. Okay, so that's pretty much simple, right? So it could be an RNN cell. It's another type way of representing it. So I think this is Italian. It's converting from Italian to English. So it's Amo Intelligenza Artificiale. I love artificial intelligence. And you're computing the loss for each of these outputs because this is a sequence-to-sequence model, or in other words, as we covered it, many-to-many model. Okay? So this was a pioneering study, but this gave a lot of ideas to researchers. And you can apply this to question answering, or I don't know, paragraph summarization, text summarization, or I don't know, sentiment analysis. All NLP problems, I mean, could apply to this encoder-decoder architecture. That's why the encoder-decoder architectures evolved until they hit transformers in 2017. Okay, so just like I said, you can just apply this to different problems like machine translation, text summarization, chatbot, anything you can think of. Or other type of categorical data as well. I mean, for example, text is a categorical data because there are words, and words are not signals. They are some categories of expression. I say categorical because a word is another vectorial representation. It's not real numbers. In the end, we convert it to real vectors so that we can feed them. It's called word embedding, and we are going to see a realization of it in the next hour. But in the end, they are categories. But you can think of other categorical sequences. For example, I don't know, the bank transactions, or because one of you is working on that stuff, my student here. Or you can think of other things as well. They will still apply to NLP's encoder-decoder sequence-to-sequence problems, guys. Or, again, we can get back to the previous week and we can talk about CNN plus RNN architectures. Doesn't matter. Then you would be stepping out of the NLP world, but still, half of your network would be recurrent. And we'll call that pre-processing and the encoder and the decoder, guys. Okay, before I finish the slides, I'm going to talk about the recurrent autoencoders. I think this is a very important title. How we can use them and why we can use them. To begin with, I mean, LSTM autoencoders or recurrent autoencoders in general are an implementation of the autoencoders for sequence data. So when you say an LSTM autoencoder, it's just simply you're using an LSTM for the encoder and an LSTM for the decoder. Just like the machine translation example, okay? But what you're doing is, instead of using an input-output sequence for a specific problem like machine translation or chatbot, what you're doing is, you do the same thing what you do for encoders. The input and output are the same. The input and the ground truth are the same. So when you feed a sentence, you need the same sentence back. Or it doesn't have to be a sentence. For example, you're trying to monitor the transactions between banks. So when you feed this categorical sequential sequence data to an encoder-decoder LSTM. And when you train it in a supervised fashion, where the ground truth is the input sequence as well, what you would be obtaining as the internal representation of that autoencoder is a latent representation for the common features that define the training set. Okay, so imagine you want to create a latent representation of a training set of sequence data. Okay, then you would use these autoencoders. And autoencoders are also called self-supervised as well, because you're supervising it with the input data itself. So once fit, and you can train it, the encoder part of the model can be used to encode or maybe compress. I mean, autoencoders were traditionally used for compressing the signals in engineering. But we do not necessarily do it to compress it. We are trying to do it to carry it to a higher level representation. And you can, so that you can use it for data visualization and stuff. Actually, although autoencoders are trained in a self-supervised fashion, once you train them, autoencoders are widely used for unsupervised problems. For example, what kind of unsupervised problem we can use? So you have a corpus of training data, you train it, sequential data, some sequence of bank transfers, you just feed it to the autoencoder, and you have a latent representation. The latent representation will carry the common features of your training data. So any data that is somewhat similar to your training corpus will be reconstructed successfully, compared to a type of data which is an outlier to your training set. So here you can define a model, a problem where you can differentiate an outlier from a type of sample which is similar to your training set. Okay, this is a type of unsupervised problem, for example. And actually, it's being widely used in unsupervised problems. For example, this is unsupervised learning of video representations using LSTMs. They feed videos, and they categorize videos. They feed videos with a bunch of samples, and they kind of categorize videos according to how well they are reconstructed. Because in the end, it's going to be reconstructed, not entirely correct, right? I mean, we don't expect the LSTM encoder to reconstruct that data exactly the same. This is, in this case, it's a CNN plus RNN, RNN plus CNN advanced architecture. So this is a bit like not only RNN. So in the encoder you have a CNN, then an RNN. Then in the decoder you have an RNN, then a CNN to reconstruct the data. It's a bit complex example, but in the end what you're trying to do is you're trying to reconstruct the input sequence, but you don't do it perfectly. So that not being perfect is a signal of, is a sign of how your sample resembles your training data. And that resemblance can be categorized or clustered to give you some unsupervised results. And the very common example is the anomaly detection, guys. This is a very recent subject, doing anomaly detection using LSTM encoders. So what you do is, you have an encoder, which is a recurrent encoder. And your input is a sequence. And in this figure taken from some, I don't know, this is CFAR10, no, it's not CFAR10, it's MMI711 dataset. But you can apply it to sequence models. So it is like, sorry about that, guys. This is, okay, so hence the deconstruction error will be high. Let me just use this way. So you feed a sequence, just like the bank transactions example. You're trying to, for example, detect anomalous bank transactions. What you can do is, you have a bunch of normal transactions. You can train an AutoEncoder, recurrent AutoEncoder, where the encoder and decoder are separate LSTMs, with normal sequence of transactions for a person, then you can check the reconstruction error to see if it's an anomaly, because you would expect that a data which is similar to your training set, which is kind of a normal transaction, normal sequence of transactions, I would say, would be reconstructed with less error. However, an outlier would be reconstructed as with higher levels of error. So this is a nice example as well. I mean, one of you is working on this stuff, but if you care to work on an unsupervised problem on sequence modeling, I strongly recommend you use LSTM autoencoders in your project in this course or in your thesis. So this is a very, very nice tool. Okay, so for example, an LSTM autoencoder can be used to detect grammar errors in a sentence. You feed the sentence and just they do it in a supervised fashion, but the grammar can be learned by the internal representation as well. Okay, so these were my slides. What are we going to do next week? We have the midterm at 8 o'clock today, 8 p.m. It's not going to be difficult, guys. I mean, you'll have time to do it and you'll have open sources. So if you did understand the very meaning of recurrency and recurrent neural networks, you will have no problems with the midterm, in my opinion. And after the midterm is week 7, and after the midterm, it will be week 8. We'll have 5 weeks, 8, 9, 10, 11, 12. Because week 13 and 14 will be your presentations. In those 5 weeks, we are going to be talking about attention. We are going to be talking about transformers. I want to talk about neural ordinary differential equations as well. So that's it. That's what we are going to cover. By the way, we have the proposals, and I'm expecting you to upload them in 2 weeks as well. So, but if you have anything to discuss about those proposals, I'm ready to answer your questions as well. Okay. And then after the break, we're going to go over a code. Any questions?
Hocam sınav nasıl oldu şimdi?